All right, so now that we've done secant, let's go ahead and go to cosecant. Oh, I just remember one thing I forgot to mention to you when I did that, right? Notice that the period follows the period of cosine. So cosine does everything it's going to do from 0 to 2 pi, which means secant's going to do everything it's going to do, all right, which was right there, all right? So it's a classic cosecant graph, this part, and this part from 0 to 2 pi. So unlike tangent and cotangent that had a period of pi, we're back to the good old period of 2 pi here. And then you can expect the same thing for cosecant. So since cosecant is the reciprocal of sine, the period of sine is going to basically make the period for cosecant. So we're expecting a 2 pi period here. Again, analyzing this, we got to worry about when that bottom is 0. So when I go through a full rotation on my circle, right, sine is 0 here and here. So x equals 0 and x equals pi. So what this means is that we're going to have vertical asymptotes there. So without graphing anything else, right, so if we just took that data there, okay, so we have an asymptote at 0, and somewhere down the line will be pi, and we'll have another asymptote, and of course somewhere down the line will be 2 pi, and we'll have another asymptote, all right, and this would actually continue to go on, right, so even at 3 pi, we'd have another asymptote, and at negative pi, we'd have another asymptote. And the reason being is because sine is equal to 0 at all those locations. So in the first rotation, what are some other nice values that we can take advantage of? Well, we already have 0 pi and 2 pi taken care of. So what about pi over 2 and 3 pi over 2? Well, pi over 2, sine is 1. So 1 divided by 1 gives us a 1. This is an asymptote, an asymptote, and an asymptote. And at 3 pi over 2, sine is negative 1, so 1 divided by negative 1 is negative 1. So at pi over 2, we're at 1, and at it's pi over 2 and 3 pi over 2, we're at negative 1. Okay? So again, kind of hard to see what's going to happen with the asymptotic behavior that we just saw. You can kind of anticipate it going up in this direction. But let's just be sure. A nice value for sine is pi over 6, right? Or what you guys know as 30 degrees. At 30 degrees, sine is equal to a half. So 1 divided by 1/2 would give us 2. All right? So at pi over 6, somewhere in here, right, we're going to be equal to 2. So this graph in this direction is going and following that data point. Over here, if we did 5 pi over 6, 5 pi over 6 right there, that's also equal to a half. So we'll also be equal to 2 right there. Okay, so there's what's going to happen to the cosecant graph from 0 to pi. In the next level, you'll notice that we're already negative, and so this puts us in quad 3 and quad 4. So you can anticipate, right, 7 pi over 6, well that's negative 1/2, multiplied by the reciprocal, well negative 2, and so 11 pi over 6, I would expect the same thing. So here and here we got a negative 2 and a negative 2 respectively. And so it's a little bit easier to see than secant, but over, again, from 0 to 2 pi, all the action is going to take place because in the next interval, we're just going to repeat. The next interval, we're going to repeat. Over here, we're going to repeat. Over here, we're going to repeat. So basically, everything we need to know is in that first cycle from 0 to 2 pi, and then that's a classic shape of our secant graph. So, cosecant graph. So a little bit easier to remember than our secant graph. Get those straight. Okay, in terms of analyzing this, again, we can see that the domain of this function, we're basically talking about all x not equal to multiples of pi, right? N is equal to any integer. So at any multiple of pi, whether it's positive or whether it's negative or positive or odd or even, sine is 0. So we're going to have a vertical asymptote. So all domain. The range, again, is something we saw before, but now we can visually see it. The range is anything below -1 and including it, anything above 1 including it. So at a low point we're at 1, at a high point we're at -1, and then everything below and everything above it respectively. Right? We also see that we do in fact have extrema. Right? We have some local minimums occurring, right, at basically all the multiples of 3 pi over 2, or the odd multiples, right, of pi over 2, and again is any integer. So that'll make sure we're an odd multiple. So pi over 2, 3 pi over 2, 5 pi over 2, all that good stuff. And we have a local max, right? The local maxes, right, are occurring also at other multiples of 2n plus 1 and pi over 2. All right, so I guess we can kind of distinguish from one from the other, but we basically have local min, local maxes at odd multiples of pi over 2. This is also what we call an odd function. Okay, mathematically speaking, that means that f of negative x is equal to negative f of x. So that basically means that the cosecant of negative x is negative cosecant of x. And you can kind of see that if we do the double flip, right? Flip this down and flip it over, we got the same graph. Or if you rotated this graph 180 degrees, this part comes over here, this part comes over here, right? That part comes over there. So it's a true rotation around the origin. Or some students like to see the double flip, right? Flip this up, flip it over, right? Flip this up, flip it over. We'll get the same graph. So it is an odd function, which should mimic what sine is, because we know that sine's an odd function. And then last but not least, the period is 2 pi. All right, it mimics what the sine does with regard to that. All right, 2 pi. Again, a lot to memorize, a lot of data points to think about. And so it turns out, let me go to my black pen. If we just go to sine, sine starts at 0, goes to 1, comes back at 0, goes to -1, and comes back to 0. So in black is my graph of sine x. And again, you'll notice that where sine crosses its equilibrium, right, in this case the x-axis, cosecant has a extrema, or excuse me, a vertical asymptote. Where sine is at a high point, the cosecant is at its low point, and where sine is at a low point, the cosecant is at a high point in terms of local extrema. So again, we're going to be able to use the graph of sine and our knowledge of sine from section 4.1 and 4.2 to actually help us with our graph of cosecant. We'll just have to talk about the data points in the first rotation. So that'll basically help us out there. But in general, there's basically your graph of secant, all right? Cosecant. It does look a little bit like cosecant. It does look a little bit like secant. Spit that out. But everything has been shifted over, and that shouldn't surprise us because of the cofunction identity. We know that secant and cosecant are theta minus 90 from each other. So they're basically a phase shift away from each other. And so if you just took this graph and shifted it over pi over 2, you get this graph. Or if you took this graph and shifted back pi over 2, you get this graph. It shouldn't be a surprise because we saw the same thing with sine and cosine. Alrighty, so now that we have some basic shapes, we're ready to go do some transformations. But again, let me warn you, what I'm going to use is our knowledge of sine and cosine to actually graph our secant and cosecant. And you'll watch me do that in some videos coming soon. Talk to you guys later.